Hello, and welcome to another episode of Fun Times in Statistics. I'm your host, Rochelle Barr, and we're going to be talking about Chapter 11 today. So, I'm hoping that you look at this screen and recognize some things that you have seen before, specifically when you look at the title. You're like, hey, confidence intervals. Check, we just talked about that. Hypothesis tests. Oh, yeah, definitely did those before. Means. Haven't talked about those in a little bit, but we definitely did the mean of the sampling distribution, so that kind of counts. And we did means in stat one. They're just averages of stuff. So obviously, I'm going to be doing the same things from the previous two chapters, but applying it to not proportions, but means. And if you watch the introduction video, you saw a little bit about what we're going to get up to with this. So let's start talking big deals. Oh boy, it's not going to the next one. There we go. So, the central limit theorem. We've already done this once. It says that if you sample well, aka randomly, and you sample often enough, you should be able to get something that looks normal. So, the normal model seems to do a good job of representing that variation of all the possible samples that you could possibly see. And it turns out that this means that also having a sampling distribution, we can get a normal model. Let's take a look at what that looks like. But before I go to that, I'm going to remind you of something real quick. When it comes to the normal distribution, there are three sort of defining characteristics on how this guy looks. It has the following things about it that are true. We know that it is, well, symmetric. Unimodal, so it just has one peak. And last but not leastly, it has this distinctive bell shape. We're going to be looking for all of that in the following leading example that I'm going to talk about. Alrighty. So here's what I'm starting with. We're going to roll some dice. We're not gambling today. We're just having some fun. So here's the thing. If you take a six-sided dice that's fair and toss it 10,000 times, you could get something that looks like this. So these are my number of tosses. This is the result on the dice. I'm hoping you notice that the tops of these aren't quite even. For a fair dice, you should get something that's fairly even in distribution. Now this is a little bumpy because we have random chance involved and because we're actually doing this empirically, not theoretically. Theoretically, these would all be even. All right, so take a look at this guy. Does it look normal? Nope. Does it have any of the characteristics of the normal distribution? Yes, it has exactly one. This guy is symmetric. Okay, so it's symmetric. That's it. I got like 1 out of 3. This definitely isn't looking normal. What the heck, central limit theorem? But remember, to meet the conditions to get a central limit theorem normal sampling distribution, I need to sample well and sample large enough. Clearly, using just one die and doing its sample distribution is not going to give me what I want. Okay, let's look at what happens as I increase my sample. Okay, here we go. Triangular distribution, looking better, looking good. Couple things to notice about this. I am averaging, the numbers that I see from 2 dice. So imagine if I rolled a 3 and a 3, my average would be a 3. That would show up in this rectangle. If I rolled a 3 and a 4, my average would be a 3.5. That would be an item that falls in this rectangle, and so on and so forth. So we notice first there is more rectangles because there are more options as to what you could get since I'm averaging across 2 dice. The other thing we notice is that this doesn't look like a bell shaped. It doesn't look normal, but it has 2 of the characteristics of the normal distribution already. This sucker is definitely symmetric looking. And I'm hoping you notice it's unimodal, unlike the other one. If you're unsure about the last guy, he is actually what we call multimodal, or it really doesn't have a mode because everything's the mode. Alrighty, let's try this again. By the way, totally forget the name's triangular distribution. You're never going to see it again. Da 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 da. So this is if you do a sample of size 5. How's it looking? Oh, it's got that distinctive bell shape starting, doesn't it? Okay, so this is finally starting to look normal. Was able to get this to happen at size 5. That doesn't mean that this is true for every single type of sample you might be looking at, but hey, what do you notice? This is looking pretty normal, huh? Okay, let's up the ante a little bit. Let's go to 20. Does it look normal? Super fun times. It's got the bell shape, it's symmetric, it's normal. I'd say it's even more normal looking than the previous one because if you look at the previous one, it's a little bit bumpy. It's not quite perfectly symmetric, but other than that, it looks pretty good. So, what's the central limit theorem telling us with this? Hey, no matter what I start with, and this is like the big humdinger of excitement back here, I am gonna get something that looks normal as long as I meet the whole sample well idea. So don't forget this. No matter what I start with, I am going to get something that looks normal. This is incredibly important. So like highlight this, hearts and stars. This is super important. The central limit theorem tells me I can have the grossest looking distribution in the world. As long as I sample and sample well, sample large enough and sample well, I will get something very, very normal looking. Now, the caveat to this is if you have something that starts out very, very skewed, this is much harder to do. You might need a much larger population than if it didn't start with something skewed. So I started with something that was uniform, so it already had one of the characteristics. It was already symmetric looking, so it was a little bit faster with the dice. Okay, now let's make some additional observations to this. So I'm going to go back to, oops, that's the wrong one. I want to go back to the very first slide. Aha, now for a good question for you. What's the mean? What's the center of this distribution? You're like, I want it in the middle. Like, it looks like it's 3.5. Woohoo! Okay, ready? Moving on. Back to the triangle. Hey, what's the mean? Take a minute, think about it. Where's the center? Oh my gosh, it's 3.5. All right, one more time. Hey, what's the mean? No, wait, I lied. It's more. It's like 2 more times. That's the worst looking thing I've ever written in a while. It looks like I wrote the word rum. Mean. Hey, 3.5. Ta-da! Okay, one more time. Hey, what do you think the mean is? I'm not fooling. It's still 3.5. Aha! So, this goes back to the same idea that we saw with the proportions. No matter what I do, if I use the sampling distribution, the mean of the distribution will be the center of the distribution, aka the mean is the center. So if I want to do the mean of my population, it's going to be the center of my distribution. So I do my sampling distribution, it turns out to be 3.5. Okay, other things to notice. I'm going to go back to the orange guy. Let's talk spread, yo. So you know lots of spreads. You should know 4, the variance, the standard deviation, the IQR, and the range. I'm going to be lazy and use the range, although since I'm using the mean, I should be using standard deviation. So I'm going to use the range just because it's easier to see with this one. Because I just want you to observe something. Okay, so where's this guy go from? 1 to 6. It's about a 5. Okay. Same thing with the blue guy. It looks like my range is 1 to 6, so this is also going to be a 5. If you forgot what the range is, it's the max minus the min. Blue guy, what's my range? Okay, this is a little bit harder because it doesn't quite reach 6. Looks like it's like 5, 7 to maybe like 4, 3. So this isn't 5 anymore. This is shorter. This looks like I'm going to call it 5.3 or 4.3. It's smaller. Okay, ready? Green guy. What would you say the range is? It's like 4.5-ish from like 2 something. I'll call it 2.5 to make my math easy. This looks like it's 2. Done. Again, I'm estimating here. What happens with your spread? Mean stays the same no matter what size sample I'm doing, but, so I want you to see that these means all stay the same, but my range doesn't do that. My range gets smaller as I increase the sample size. So even just look at going from the 2 that look normal. Aha, this was doing 5 dice versus 20 dice. It like over halved it. Another way you can look at this is think about the 68, 95, 99.7 rule. Where would I put the markers for that if I was doing the standard deviations? It looks like right about here and here, which means it's probably like 0.3. It's very small. Alrighty, so mu, center, mean, stays the same. Range, any type of spread I'm looking at for these, as I increase my sample size, it gets smaller. Okay, so I did that guy already. Whew. We're going to be dealing now with two distributions, the original distribution we started with and the sampling one, the one from taking repeated samples. So be thinking about the green guy versus the light blue guy I did in the beginning. They clearly do not look the same. All right, so how can I tell the difference between these two? Well, think about what an individual question would look like versus about a group. Which would be more surprising? One person in your statistics class is over 6'9", or having the average of a 100-student class being over 6'9". This isn't a trick question. It's this one is definitely more unusual. I'd have to have the whole basketball team and all their tall cousins with them in order for the average to be that. Why is that true? Because things that are more extreme, aka out in the tails, are less likely if your tails or your spread of your distribution is smaller. So be thinking like, oh, if this was my sampling distribution, the stuff that's out here in the ends, the unusual stuff, it's going to be less likely to happen because when I have a large sample, like 100, my shape of my distribution is going to be taller and narrower. So the probability in here is like super tiny, and it's even smaller. That's what's really happening there. Okay. And I already said this a little bit or hinted at it, but here we go. So what's the sampling distribution's standard deviation? Well, it's just going to be the standard deviation of the population divided by the square root of the sample size. This should look fairly familiar. So remember, y bar, that means mean of a sample. So when I'm looking at and writing this, I'm thinking to myself, oh, this is the standard deviation of a sample. So this is what we use to write the sampling distribution. Aha. So the sampling distribution standard deviation is just the standard deviation of the original divided by the square root of the sample size. This is exactly why when I went from having a sample size of 5 to having a sample size of 20, my spread, my standard deviation, got smaller. Okay, I don't know why I'm repeating myself here. Hey, that's the spread, and the mean's the mean. So, what's really going on here? Well, what I'm saying is that when I write the normal distribution, I know that my sampling distribution is normally distributed. That's what this tilde means. Its distribution is, and the capital N means normal. It has the mean, that's the mean, and standard deviation, the standard deviation of the population divided by the square root of the sample size. Remember, here we're doing samples and asking about samples, not one person in a distribution of the original. Remember, we don't know necessarily what the original looks like, but we can do the sampling distribution and look at its mean and look at its spread and determine what this is going to be. Okay, similarly, this looks a lot like what we were doing with proportions. Hello, proportions. Okay, so as you look at this, I'm sorry, I'm stuck again. I don't know where I am. It's fine. I'm here. You're there. Oh no, I clicked on it. Sorry. Oh boy, I should probably cut that, but I don't care. So when we look at categorical data, we were dealing with proportions and therefore, p's, and we came up with a sampling distribution for it and standard deviation for it, and it came out PQ divided by N. Similarly, when we're calculating the normal model for mean of population, the standard deviation comes out like this. So again, we're looking at this and being like, oh, square root of N, square root of N. Let's do this. All right, so when is it going to be sampled well enough and sampled large enough to get this happening? Couple things. We need some independence between our samples. This is something that we had before. We need randomization. This is that sample well idea. And then I'm hoping that you notice these look almost identical to the Perowin's for population proportion because they are. We need the sample size assumption. This is a statement that the sample size must be sufficiently large. Oh boy, how big does that mean? That's super vague. I don't know. Well, I do know, but we'll come back to that. And then we also need what's called the 10% condition. This is to avoid oversampling. This is just like the idea behind the 10% condition in the proportions examples. All right, the large enough condition. I know this is super vague. The idea is that if you have something that already kind of looks normal, aka it's either unimodal, or maybe it's got some symmetry, or maybe it has a bell shape, then it's already normal, then it's much smaller sample sizes will yield something normal. I had something that looked normal with using a sample size of 5. That's considered pretty small. In most cases, 5 will not be large enough. I was always told when I was a student that you had to use 20, and that was your cutoff. Nowadays, to be large enough, most of the time, we use our sample size being bigger than or equal to 30. Now, we're going to see what we do when it's under 30 here in a little bit, so don't let this panic you. Like, oh God, all my samples have to be at least that big in order for this to work. Not really. That was too loud, I'm sorry. It depends on how your original looked. So clearly I was able to do it in 5 for something that was not very skewed. Let's do an example, because I've been talking for too much. Alrighty, so according to recent studies, cholesterol levels in healthy U.S. adults average to be about 215 milligrams per deciliter, with a standard deviation of about 30 milligrams per deciliter, and are roughly symmetric and unimodal. That's important because that's telling us shape. It's already looking kind of normal. If the cholesterol levels from a random sample of 42 adults is taken, U.S. adults is taken, are the conditions to use the normal model met? All right, let's talk about this. The answers are literally on the next slide, but I'll talk you through it. Is it random? Random sample, done. Yep, okay, it's random. Does it meet the 10% condition? Well, think about this. Is 42 10% of the population? If it is, then there's only 420 adults in the United States. That seems really unlikely. Is it bigger than 10%? Nope. It's probably not oversampled. We're probably good for this condition. Is it large enough? It's 42. That's bigger than 30. We're good. And it already has some fairly normal looking stuff to it. Alrighty. So 42, large enough, yada, yada, yada. I just did all this. Why am I talking about it again? Let's continue with this example. What would the mean of the sampling distribution be? And I know that this is going to seem silly, but the mean of the sampling distribution is the mean. The mean is the mean. This will be the easiest question you come across in your homework. This is the easiest question you'll come across in your exam. Your mean. What's my mean? It's the mean. Simple enough. What's the mean of the sampling standard? What's the standard deviation of the sampling distribution? That's a little bit harder. That I'm really asking you about, what's sigma of y bar? So what's the sampling distribution's spread? Or the SD, I like this one a little bit better, standard deviation of the y bar. I also don't like my sigma. It looks kind of like a circle that I screwed up. Yeah, that's what I'm really asking about in the second one. This one is just asking, well, what's the mean of the sampling distribution? Well, it's just the mean. That's the easy one. It's just going to be 215 because that's what the mean was. This one, I'm going to have to do the standard deviation of the original population distribution and divide by the square root of the sample size. So that's going to be 30 divided by the square root of 42 because that was my sample size. So let's click to the next slide, which shows you that that's what it is. Yeah. And I rounded a little bit here. If you're dealing with something really tiny, like if this is in like, 0.00004, don't round this too much. You should do more decimal places. Anyway, so that's my mean, that's my standard deviation. Once you know the mean and the standard deviation and that this is normal looking, well, you can calculate normal probabilities on it. Like, what's the probability that the average cholesterol will be greater than 220? Okay, so we should take this and we should write it as a probability statement. Well, what's the probability that my sample's average, y bar, is greater than or equal to 220? So traditionally, if you were to do this by hand, what you would do next is change this into a z-score. So I'm going to write this as z bar because it's a sample, not really just a z. It would be greater than or equal to, I'd do 220 minus my mean, which was 215, divided by my standard deviation, which is 4 I'm going to cheat and look, 629, because I don't remember that off the top of my head. Oh, my 9's bad. And then I'd figure out what that is going to be. So I want the probability that my z bar is greater than or equal to 1.08, and you could either look that up on the table, or if you didn't want to do this conversion, this middle probability, you could just go to your calculator and use this probability calculation using the mean and standard deviation for that distribution. I have a couple videos on doing this in your example videos coming up next. All right, there's it typed, much nicer, and clearly I calculated it either using tables or whatever and whatnot. Okay, couple things that are important in this question. There is one word in here that is pointing you to, oh my gosh, this is the sampling distribution, not just a regular probability calculation, and that's this word, average. This is the thing that's pointing you to, I'm doing an average of a group of people, not one person. Watch out for this. This is the one thing you need in order to know you're doing the sampling distribution. Or if I asked you questions about the sampling distribution before it, hint, hint, wink, wink. Okay. How about another example? The mean weight of boxes shipped by a company, sorry, is 12 pounds. The average, or sorry, with a standard deviation of 4. Boxes are shipped in pallets of 10 boxes. The shipper has a limit of 150 for such shipments. What is the probability that the pallet will exceed the limit? Asking the probability exceeds the total weight of the sample of 10 exceeds 150 is the same as asking the probability of the mean weight exceeds 15 pounds. This last sentence is like reading mathematical gibberish. So think about it this way, all right? I want the probability that the pallet is greater than 150. I keep writing equal to, but that's super unnecessary. Um, and then, it wouldn't be shipped or it'd cost you extra. But this isn't a sampling distribution question. This isn't a question about an average. So what I'm saying is you need to take this and you need to convert it by just dividing by 10 and saying, okay, instead of doing the whole pallet, I'll just do average weight, which would be 15. So on average, my boxes would have to be over 15 ounces in order to exceed this weight, which makes sense. So if they're normally with a mean of 12, it's really asking you, on average, do they all together exceed 15 each? Which would be the same idea. Be careful with this. This is a common question confusion tactic. They'll give you one big object that's made up of a bunch of little objects. What you should be looking at is the average weight for all those objects because we're doing means. We're doing averages. Watch out for this. It's sneaky. There was something else I wanted to warn you about with this one. I don't know. I guess I'll think of it when I go forward. Let's do some stuff. Anyway. First, we should check conditions. There are 10 boxes in the pallet. They're random, so it's probably okay, and they're probably all independent of each other because they're not using probably just one production line. And even then, they probably don't depend on each other. 10 boxes is probably less than 10% of your population because otherwise your company is producing almost nothing, and that's kind of silly. The only thing we really can't check in here is this going to be large enough to make it look normal? So I sort of flubbed and skipped that one. This is important to do. Well, I'll say that in a minute. Anyway, so here's how you'd calculate this. You'd figure out your standard deviation. So I take my standard deviation from the population, divide by the square root of the sample size. It's 1.26. I'm sort of rounding badly here, but ignore that. And then I would go ahead and set up my probability calculation with my average being over 15. That is a typo. I didn't do 150, clearly I did 15. Ta-da. Sorry about that. So, if you want, you can erase that from your notes and I'll try to make sure I cut it out from the ones that you see posted on Blackboard. The other thing to note about this is kind of an important question. It tells you exactly how often you're going to exceed the shipping limit. So if their thing about exceeding the shipping limit is, oh, okay, if you exceed the shipping limit, then we're going to charge you extra $30, but we'll ship it anyway. You can plan accordingly for this. You know it's going to happen about 0.8% of the time. So, every once in a while, you should send them a couple extra bucks, exactly 0.8 of the time percent, and then be prepared that that's how often, you're going to give them an extra $30. So that, oh gosh, I hit a button, sorry. Oops. So you could also think of this as it's 8 out of 1,000 roughly. So, for every 1,000 boxes, you give them whatever 8 times 30 is dollars extra, preparing for the fact that, oh my gosh, I'm probably going to have to pay extra. This also prepares you for that idea too. It also tells you that, oh, if they're charging me this overcharge fee more often than that, they're up to something. Are they really actually weighing these correctly? Or is my weighing system that I'm currently using inconsistent and that's why I'm getting overcharged? So it points you at a couple different things. Alrighty. So just like dealing with the population proportion idea, occasionally you will have to, instead of using the population standard deviation, use the sample standard deviation, aka S, because you won't have the population standard deviation available. Realistically, in the real world of statistics, when you're out trying to figure out things out about your business partners and or your customers, you are not going to know what the population looks like. Trying to figure out what your entire population looks like is easy if you're a small company and only cater to maybe 10 people. But the idea is that you probably aren't doing much business then, and you might go out of business if it stays that way. You'll be looking at new markets and other things that are out there. You usually well, I shouldn't say usually, you almost always do not have your population spread. So we tend to end up using the standard error instead. Remember, standard error is not really like making a mistake. It's more of these are different by a little bit. We don't treat errors in statistics as being wrong, but rather something that's off of the original by a little bit. Just so you're aware. I don't know why I drew on that for fun. Okay. Whew. How do sampling models work? Well, the sampling proportion and the sample mean are random quantities. You don't really know ahead of time which of the ones you're going to be getting. So one of the basic truths you're going to see is that sampling distributions arise because samples vary. And although we can simulate the sampling distribution through the central limit theorem, it really saves us the trouble of actually calculating the physical mean and the physical proportions by themselves. But this can be problematic. Let's look at a skewed example. So if you take something that's skewed, so this is a skew model and I just do the smooth continuous distribution, and you sample repeatedly, so here's one sample, here's two samples, here are three samples, they do look like the original. They all have some skew to them, some more than others. This one's worse than these two. Okay, so as you look at this, I'm hoping you notice that, oh, so my samples tend to look my original, which means that if I sample often, I might not actually get something that looks normal really quickly if it has such a severe skew. Let me show you how this looks. So here's a sampling distribution for that distribution that I just showed you on the previous slide. And if you look at it, it's not quite normal. It's a little too hefty in the middle. It doesn't quite have the bell shape yet. I could fix this by just repeating more and more and more and more and more, or picking a larger sample size. But I'm hoping you notice that since samples vary, they fall out in very different locations. So remember, when you're doing the normal model, this is an estimate that only is as good as your work and knowledge about what is happening with your original. But it starts to look normal. You just got to do it good enough for a skew. Okay. So, remember, we don't know necessarily the standard deviation of the sample, then we're going to estimate it with using the standard deviation of the sample. I just said standard deviation of the sample twice. If I don't have sigma, the population dude, I use the sample dude, S. Yay. We make the assumption that our standard deviation of the sampling distribution is well estimated by the sampling standard deviation and form this normal model. Woohoo! Now, since I have a sampling distribution that looks normal, that means I can start out at my sample and add and subtract standard deviations in order to get confidence intervals. Yay! Here we go. So, one of the things I've mentioned before is that when you look at any confidence interval, it's always your estimator plus a margin of error. They all look like this. We're going to learn lots of different confidence intervals in this class, and they always maintain that same fact. Okay, so this first top part, this is what the proportion one looked like. Oh, I'm estimating a proportion and subtract my margin of error. My margin of error was my critical value, z star, coming from my confidence level, times my standard error. This also could be standard deviation if you know the population standard deviation. Similarly, our confidence interval for the mean is going to be, hey, I'm going to take my mean, y bar, and add and subtract my margin of error, which is going to be a critical value times standard error. I'm being vague here on purpose because I'm like, oh my gosh, what critical value am I going to use here? Things! Oh, things. All right. So here's the thing. If your standard deviation is given, aka I know the population standard deviation, I'm just going to be using this standard deviation. If it's not given, I'll be using the one from the sample, and then I'll be dealing with the standard error. We're going to assume these estimate each other well, but that doesn't necessarily mean that this is the best move in the world. This can cause some problems. The first person to investigate this was William S. Gossett. So he had the problem of, oh my gosh, I need to drink beer and be happy, and I'll say that in a minute. But he noticed that when you end up using the standard error, often your shape no longer looks normal. So he created this new model called the student t-distribution, which is a model that has a bell shape, but it also has what we call fat tails. So it's slightly different from the normal distribution, but accounts for this difference in spread. And the student t model looks different depending on, well, a different parameter called the degrees of freedom. The degrees of freedom is related to the sample size. So keep in mind the t-distribution looks different depending on what sample size you're dealing with. Now I'm going to tell you a story. William S. Gossett used to work for the Guinness Brewer Company, and the problem he was having is that, oh my gosh, we need to figure out the alcohol content of our beer in order to be able to manufacture it and sell it, because if it was beyond certain aspects or beyond certain amounts or percentages, it wasn't allowed to be sold, or, your customers would get mad because they don't get drunk. I don't actually know if that's true or not. I do know that if it didn't meet certain specifications, you weren't allowed to sell it. So that's kind of fun. So the problem was, if you sample multiple times during the brewing process and you sample large so that you get a good sample, you have no product to sell. That's bad. So Gossett was dealing with lots of small samples, and he noticed that for using the standard error, his distributions for these small samples looked different, but they still had a bell shape. And that's where the student t distribution comes from. If you're wondering why it's called the student's t distribution, it's because the S in William S. Gossett stands for student. So I'm hoping you learn that from this little story that you shouldn't give your kid a terrible name, and that beer can help you do statistics. I don't know. I don't know what I'm saying anymore. All right. Hopefully, I had some fun in the middle of my lesson. Moving on. This is a little bit about what it looks like. So in the dotted line, I have the standard normal curve. In the solid line, I have the William S. Gossett T distribution, which, if you notice, is a little bit bigger on the ends and a little less peaked or round in the top. And this is what we call fatter tails. So these T distributions have a larger tail to them. Let's use it. So, what's the standard error of the mean? Hey, what's the I just started reading this in the middle. Data from a survey of 25 randomly selected customers found that a mean age of 31.84 years and a standard deviation was 9.84. Oh no, I'm going to have to redo this. Reschedule. Okay. Let's start over. Okay. Data from a survey of 25 randomly selected customers found that the mean age of 31.84 years and had a standard deviation of 9.84. So this is talking about the sample. We're going to find the standard error, and then we're going to ask ourselves, how does the standard error change when I use a sample size of 100 instead of 25? Let's take a look at this. So I'm just going to take my standard deviation of the sample, divide by the square root of the sample size. I get 1.968. I take the standard deviation of the new sample size of 100, and I divide. What do you notice about these two? I'm hoping you look at this and you see that, oh my gosh, going from here to here, it looks like I just divided. Oh, this is not good. I shouldn't do that. Just divided by 2. Or if you take this and you double it. It looks like I wrote 0.2. 2. Aha! Why? Well, I'm doing a square root. How many times does 25 fit in 100? 4 times. Take the square root of 4, you get 2. That's really what's going on. And it's in the denominator, so it's like you're dividing by 2. Okay. Whew. So how are we going to use the t model? Exactly the same as the z. The only difference is that t depends on your degrees of freedom, or n minus 1, which is the degrees of freedom. So how do you do this? Sample minus mean, divide by standard deviation. Remember, I'm doing this on a different distribution now, not the normal, but it looks exactly the same because it looks normal. All right, so how do I do a confidence interval? I'm going to do my mean plus or minus my margin of error, where my margin of error is calculated by my critical value times my standard error. This may look like symbolic nonsense. It's going to make tons of sense the second I use a calculation to do this. So again, nothing new yet, just a slightly different way of doing it. Okay, so you might be asking yourself, why n minus 1? Well, a couple different reasons. We're using the sample mean instead of the true mean of the population, which means the mean has already appeared in all the differences that we're doing. So when I'm adding these all together, I'm overcounting by 1. There's the simple version of this paragraph. Feel free to read it. Okay, so just like dealing with the z value, our confidence levels will cause us to have a different t. But the difference is, on a student's t model, it's different for every single sample size, so it gets a little complicated. So we're going to use technology more often than not to do this, rather than using tables. I'm still going to show you the table in case you want to do it. I also will post a copy of the table, but it's usually generally just easier to use Minitab or your calculator to do this. Okay, so we're going to show a typical t-table on the next slide. There's also one at the back of your book, and the Appendix C, I do believe. And we use DF to stand for degrees of freedom, and it will be different depending on your confidence levels. And I'm going to show you what the infinity row looks like too. So down we go. Ready for the model? Or sorry, the table? All right. This is what she looks like. It's a little confusing to read. Okay, so first of all, I want you to draw your attention to the bottom of the row. This is the infinite row. So here's 80, 90, 95, some typical values for your confidence levels. And then right above them, you should see some things that look familiar. Oh my gosh, that's the one for 95 for T, and for, 90 for T, and 80 for T. We don't really use 80 that much. Oh, this is because when your degrees of freedom get specifically large enough, T approaches Z. They start to look the same. So if you accidentally use T when you should use Z, it doesn't matter because T is going to get close anyway. All right. Now, take a look at what this does. There's this options up above for a two-tail and a one-tail. This doesn't matter so much for when you're doing confidence intervals. For confidence intervals, we're just going to be using the two-tail anyway. For when we do hypothesis testing, this will matter. Am I doing a right-tailed test, a left-tailed test, or am I doing a two-tailed test? Let's do an example because the examples usually make this a little better. So let's say we have data surveyed from 25 randomly selected customers with a mean age of 31.84 and a standard deviation of 9.84. I'm using this example a lot. Enjoy. We're going to construct a 95% confidence interval for the mean and interpret what the interval means. This is very important. We did interpretations with proportions too. Same deal here. Okay, so let's construct this guy. So I need my mean for my sample plus or minus my critical value times my standard error. So I'm just plugging in numbers here. So there's my mean, there's my standard deviation, there's my sample size. Where'd this T come from? Oh my gosh, I don't know. Just kidding, let's find it. Okay, so I'm doing a 95%er here, and I know that my sample size is 25, which means my degrees of freedom. So here's a standard t-table in front of you, and I'm going to scroll down to the 24th row because my degrees of freedom is 24 because my sample size is 25. And I'm going to look along here until I hit the 95%er, which is the center column. So center column, 24th guy, 2.046. Again, if you use technology to do this, you will never actually have to go to a table to do this. Fun fact. So there's where it came from. Okay, back to the question. So as you look at this, hey, there's where those come from. Multiply first, and then add and subtract. There we go. Lower, upper. Remember, these are averages. They are means. They're slightly different from what we're used to using before. So we're going to interpret the 95% confidence interval now. We are 95% confident that the true mean age of all customers is between 27.78 and 35.90 years. Couple things that get mentioned in here that are different from when we did proportions. We're always going to make sure this has context, but we're always going to be talking about how this is the true average, the mean. There has to be the word average or mean in there somewhere in order for this to work. Lastly, we always are going to mention our units. Gotta include my years in there because this is a quantitative variable. It needs to have units. Fun facts. All right. As always, you should check your assumptions and conditions. Check yourself before you wreck yourself. I'm so hip, yo. Randomization, since this data was randomly collected, we're good. 10% condition, as always. Oh, sorry, I skipped around. The last thing we need to talk about is what we call the nearly normal condition. When it's close to being normal, we don't need a large sample size. But if it's not, then we probably do. What do I mean by that? Well, here's some conditions for when you're going to be okay. So if you know that you're going to be dealing with something that looks normal, and you don't have any outliers, it looks very, very much like what you should expect, then you can go ahead and get away with a small sample size. If you're not sure If it has some stuff that works, usually we use between 15 and 40. If you have a huge skew, you're probably going to use something bigger than 50, but 40 to 50 are safe usually unless you have extreme skew. So if you're looking at something that's particular between like 40 and 50, like my 42 example earlier, you're probably safe. It's probably going to look normal. Okay. We're going to do more nearly normals later. So here's a really skewed population, really skewed sample. It's extremely skewed. This is 500 CEOs. So there are several people who they may be the CEO, but maybe it's their own company and they don't have a huge salary, or they're electing not to take one because they're philanthropic. And then there's people who make a little bit more than others. So this is very inconsistent. It's very much a skewed distribution. Salaries are very typical for skeweds. So you might ask yourself, well, what size sample do I need to get this to look normal? Well, I had to do 100 to get it to even look slightly normal. But even then, as you look at this, it's a little one-sided. It's not completely symmetric. So I might even have to go larger for this to look nearly normal. So like I said, up above 50, but if you have severe skew, 50 might not be enough, just so you're aware. Here's that sample data that we did the example from earlier with the age of customers example. It has some of the characteristics we want. It has unimodality. It's almost symmetric. So I would call this nearly normal, or close enough to nearly normal to where we would be okay. So in checking the assumptions and conditions on this sample, I'm going to call it okay. It's not great, just so you're aware. So if I was reporting these results to, say, like the CEO, there he is again, or she, I would be careful to make sure that I mention something about how it's close, but it's not quite perfect. It's nearly there, but not great. All right, so independence and randomness. Customers are random, that's pretty true. And they're pretty independent from each other unless they arrive together and buy things together, which, that could happen. But since it was random, you're probably okay. This is probably fewer than 10% of your customer population because it's not a very big sample. It's only 25 people. And by looking at that histogram we just saw for this sample, it's unimodal and looks pretty symmetric. So it's got enough to meet the nearly normal. So we were okay to do a confidence interval on this sample. And this is all the things you should check before you know for sure that you can do a confidence interval on it. All right. Whew. Be careful. Confidence intervals are about the mean. It's not about the individual observations, so don't mention your sample because your sample is clearly going to be in there no matter what you do, but it's really about trying to estimate the population mean, not the sample mean. You know the sample mean, you just calculated it. Anyway, make sure you mention your confidence level. I'm warning you for some reason in here. This is called a one sample t-test for the mean, and we can also use them to do hypothesis testing on the sample distribution. So this is going to again feel like deja vu because we're going to be performing a hypothesis test, but we're using means also. So how do you calculate the test statistic? It's just like you would do before, but it's on T, not on Z. You can do Z's, but you have to know that your population standard deviation and you have to know it looks normal, which probably isn't going to be true for real data. So instead, I'm going to be doing the T distribution stuff. It's still calculated the same way. My score minus my mean divided by my standard deviation. That's going to be how I calculate my test statistic, and I'm going to use that to do my p-values. So this looks absolutely the same as doing a hypothesis test for a proportion, except for everything you're doing is about means. So let me take you through one. Shopping patterns. A manager of a small convenience store randomly samples 20 purchases from yesterday's sales. If the mean was $45.26 and the standard deviation was 20.67, is there evidence that the overall mean purchase amount is at least $40? What are the hypotheses? What conditions must be met? Let's find our test statistic or T statistic. Let's calculate our p-value for the test and then use that to draw some conclusions about sales. Conclusions follow the same way also. I'm going to compare it to a standard level of significance and decide whether or not I have something that either supports, fail to reject, or does not support, reject my hypothesis, my null hypothesis. So we look at this and we're like, oh, well, what are my hypotheses? It's at least $40. There's my alternative hypothesis staring us in the face. So my null is going to be that it is equal to $40 and that my mean is greater than $40. Again, these are about means. You need to make sure that you write that these are means, not p's. Be careful. One of the biggest mistakes I see people make is that they're so used to proportion testing from stat 1 that they want to write p's here. No, this is the one about means, and it's going to become even more important when we start to do other tests, that you make sure that you clarify what you're actually testing. So if it's about means, it should be means. If it's about proportions, it should be proportions. We're going to have even more of these, so we need to be specific. Are the conditions met? Yay! We know it's sampled randomly. Check on that one. 20 purchases is probably less than what you make in 10% of all your purchases at your store. Otherwise, you're probably going out of business. The sample size is small, so we should be highly suspicious, but I checked the histogram, and I'm not even going to draw it on here. It's unimodal and symmetric, so it's probably okay. In fact, it's much better than the one you saw previously for the age data, so it's good enough for us to go ahead with doing the hypothesis test, because this will look nearly normal, and therefore our sampling distribution will look normal. All right, so first we're going to calculate our t-statistic. So I do my mean minus my sample mean minus my population mean, my hypothesized population mean, and divide by my standard error. So this is how you would calculate that. You should take a moment to actually calculate this to make sure you get the same values that I do. If not, we need to talk about calculator usage. You should get a hold of me. And then we're going to calculate our p-value. Now remember, p-value comes from pointing where our alternative hypothesis seems to go. So here I'm looking at greater than, because I want to see if it's at least 40, aka is it 40 or more, aka greater than 40. So I want to do greater than that t-statistic. So since I'm using 19 degrees of freedom, what I would then do is, pull out Minitab or my calculator and calculate this p-value. I'm going to show you lots of ways to do this, so I'm just going to skip it for now because this video is already 46 minutes long. What can we conclude about the overall mean sales? Hey, hold on. How big is that p? Is it bigger than 5%? Yup. Oh no, that means this is pretty likely, and therefore I'm going to fail to reject. Aha, there's insufficient evidence that the mean sales is greater than $40. Darn it, it's not greater. You could also say this in other ways. You might look at this and be like, well, damn, why didn't she say something like the evidence points towards it being $40? Because the question asked was, is it at least $40? I want to actually answer that question while I'm drawing my conclusions. So I'm saying that, hey, it doesn't look like it's greater than $40. So be careful. There's some sneaky ways you can write your conclusions that follow answering the question, but might not look like what you directly expected to see. Alrighty. Hey, what's the margin of error? Test statistic times spread. We've seen this before. I don't know why I didn't put this earlier. I don't know. We always know that larger samples usually cost more money to gather because, well, they're larger and you have to be able to contact more people. It takes more man hours and so on and so forth. So what you might ask yourself is, oh, well, what's the smallest sample size I need in order to make sure that I'm within certain bounds for my error? Woohoo! So the equation has several values that we don't know in margin of error. Yeah, you don't know your spread usually, but we can use sample size, the sample spread, to do that. Usually a good guess is good enough. This is horrible because we are guessing a little bit. So we'll use samples, it'll be fine. But more often than not, we're not going to know. The other thing we're going to do is, since you need to know the sample size to figure out t, we can't really find the critical value. So instead of using t when we're calculating our sample size, we're going to be using z. This is the only time you should appropriately do that. So if you don't know sample size and you're trying to find sample size, you can use z instead of t. So here's how you would do that. Woohoo! Your sample size is approximately going to be the critical value z times your standard deviation divided by your margin of error squared. This is simply coming from taking the margin of error equation. Sorry, I'm having pen issues. Margin of error equation. Yep, margin of error equation. I should have just written that and then said it. Taking the margin of error equation and then solving for n. That's where this came from. If you'd like to take the time to do the algebra to do so, you probably should, because algebra is fun. It's like playing chess. Good times. And math things. So it's not too big of a surprise. But, the one change, I use Z instead of T when it comes to doing mean calculations. Okay. Keep in mind, these calculations are never exact. Okay? They're approximate. And the other thing is, I always, always, always am going to be rounding these up in order to make sure I'm within certain bounds. So keep that in mind. So, as always, round up. Woohoo! Let's see an example. All right, so data is plural, whoops. Data from a survey of 25 randomly selected customers is found to have a mean age of 31.84 years. Oh my gosh, I'm using this example again. I wrote this being a really boring person. I should have came up with some more stuff. And had a standard deviation of 9.84 years. A 95% confidence interval for the mean was found to be 27.78 with 35.90 with a margin of error of 4.06. How large of a sample is needed in order to cut the margin of error down to just being 2? So I know my margin of error, it's 2. Woohoo. I know my confidence level, I know my mean, I know my standard deviation. We're just going to plug those into the equation and come up with what this is. All right, so margin of error, 2. Standard deviation, bam. 95% or Z is 1.96. Show that in there. You square it, you get 92.99. We're gonna actually use 93 people. Pretty clear? Okay. All right. Now, that is all. So we've learned to do a lot of things. All of them for means, but all of them repeats from doing proportions. So this is not new stuff. It's just a different application of it. What can go wrong? You have to decide when to use the student T. There's no quick and dirty way to do this, but more often than not, you will be using T, not Z, because we usually don't know the population standard deviation. You should investigate outliers. They're there. You should look out for them. They're scary. I don't know what I'm doing. Watch out for bias in measurements because, well, if it's a biased sample, you shouldn't be using it because you probably won't get good results, number one. And number two, it's not going to meet the conditions to be able to use the sampling distribution. Make sure your data are independent. All right, so what have we learned? Well, we learned about the sampling distribution of the mean. We applied the central limit theorem. We noticed that they all have the same mean. It's the mean. And that the standard deviation, or standard error of it, is just the standard deviation divided by the square root of the sample size. Or, I screwed up, or the spread gets bigger. All right. Confidence interval for the mean has the following form. It's always the same. My estimator plus or minus my margin of error. My margin of error is calculated by using degrees of freedom in the t distribution with the standard error. I use t from tables or technology. We're going to use technology. Alrighty. Check your assumptions and conditions before using any sampling distribution or inference. Make sure you write out clear summaries to interpret your confidence interval, and make sure you actually answer the question asked from you. Be able to perform a hypothesis test for the mean, so make sure you're careful. Your null always has the same form. Your test statistic always has the same form. Your alternate is the thing that might change, so be careful. I say be careful too much. Peace out, home.